Uh, now let's discuss regarding linear shift invariant systems, which is
Start with rupees.
okay. Let's discuss linear shift invariant systems now. So let's first look at what is a linear system here. This is something, an idea from uh, maybe you might have come across this in signal processing or control systems. Let M and M. So we'll be looking at linear systems in terms of an image perspective here, mostly as imaging systems. So let M and N be pixel locations. Uh, yeah, M and N belongs to the set of integers. Okay. So these are the indices, pixel locations. So Fn of Mn and F2 of Mn are two images. These two images are given to a linear system, right? Then linear system T, which takes in these images and gives some output. So these system, I mean, the system which we are giving, to which we are giving these images as input, this is called to be a linear system if it satisfies two properties. One is suppose we add these two images, f1 of mn and f2 of mn, and give it to this particular system. So what this particular system does is applies a transformation basically on the input image or the sum of images. So if you sum it up, sum these two images, which can be treated as two signals, because basically images are also signals, then the output of that sum of images is basically the sum of the individual outputs. Okay, so this is a T of Fn of m, that's T of F2 of m. This is one property which has to hold. Another property is we're scaling the image which we have by scalar alpha, and we are passing to the system. Suppose we already know what the transformation of the unscaled image is, then which is given by T of F of Mn, then what we have basically have to do is just take alpha scalar and multiply it with the already existing response. So these two properties has to hold. If these properties holds, then T can be called as a linear system. So we can combine both this, excuse me, both these properties together, um, and write it like this: T of alpha of f1 of m plus beta of f2 of m will be alpha times T of fn of mn plus beta times T of f2 of mn. This is a general condition which we have to check whenever we are looking for. We have to check whether the system is linear or not. So another idea which comes in tandem with linear systems is something known as time invariance or shift invariance. So basically, it is also in a similar setting. We have a signal f of mn, and we are passing it to a system. After the transformation, it gives us the output g of mn. So that the corresponding system is called shift invariant or time invariant uh, in temporal signals. In images, we mostly are concerned about the shift invariance because we are working in the spatial domain. So T of f of m minus k and n minus l, where k and l are the corresponding shifts in the spatial domain, then the output is also shifted by the same k and l. So what it means is if we know the response of an unshifted image and we shift that image by some value, and the corresponding output, we just have to do the shift out. The output image also has to be shifted by the same value if it's a linear system. Sorry, if it's a shift invariant system. So if both these properties hold together, then it is called a linear shift invariant system. Okay. Yeah. So we'll discuss that. And a very important property of linear shift invariant system is called convolution, which we'll discuss sometime. So before we discuss convolution, we have to discuss something known as a discrete impulse function, or which is popularly known as a Kronecker delta function. Kronecker delta function. So how the Kronecker delta function is defined is when delta of mn is 1 when m comma n is equal to 0. This is a 2D case which I'm mentioning here, and it is 0 otherwise for all the integer values. Mind, we taking only the integer values here because we're taking the discrete case. So if for all integers apart from 0, its value 0, and at m is equal to 0, m and n is equal to 0, it has a value 1. So this is how the Kronecker delta is defined. So, yeah. So we have to also look at what is known as an impulse response. So we have seen what an impulse is, sigma, sorry, delta of mn. And we've seen a system which takes an input f of mn and gives a corresponding output g of mn. So impulse responses, instead of f of mn, you are giving a specific function which is known as delta of mn, which is a Kronecker delta. Its corresponding output is known as h of mn. Okay, and it happens that such that suppose we need to find g of mn. Okay, a particular response of a system. Okay, maybe we can discuss this as a next lecture.